Hi everyone, and let's talk about the 2D materials beyond graphene, the next atomic revolution. When graphene burst onto the scene, it redefined what we thought was possible in material science. A single layer of carbon atoms, stronger than steel, lighter than paper, and more conductive than copper. It was hailed as the wonder material, but even wonders have limit. Graphene has no band gap, which means it can't easily switch electricity on and off, a vital property for digital electronics. So, scientists around the world began searching beyond graphene, and what they found sparked a new revolution, an entire universe of two-dimensional material, such as a few atoms thick each with its own unique superpower. Meet molybdenum disulfide, or MoS₂, a crystalline sandwich of molybdenum atoms between two layers of sulfur. Unlike graphene, MoS₂ is a true semiconductor. It can switch between conducting and insulating states just like silicon, but in a layer that's only 3 atoms thick. This property makes it perfect for transistors, sensors, and flexible electronics that could wrap around your wrist or fold into your pockets. MoS₂ is also highly sensitive to light, which means it can act as a photodetector, turning light into electrical signals, or even help split water molecules to produce hydrogen, a clean, renewable fuel. It's thin, strong, stable, and incredibly versatile, a rising star in nanoelectronics and energy catalysis. Next up is hexagonal boron nitride, or HBN, often nicknamed white graphene. At first glance, it looks almost identical to graphene. Same honeycomb structure, but its personality couldn't be more different. Where graphene conducts, HBN insulates. It's one of the most smoothest materials ever discovered, resisting heat, chemicals, and corrosion, even at extreme temperatures. Think of it as the Teflon of the atomic world, forming ultra clean surfaces that protect and support other 2D layers. In the advanced photonics, HBN even hosts quantum emitters, tiny defects in its lattice that release single photons on demand. This makes it a powerful candidate for quantum computing, secure communications, and on-chip photonics. It may be quiet and colorless, but HBN is the backbone of many futuristic nano devices, the invisible hero that keeps everything stable. And then there's the phosphorene, the two-dimensional form of black phosphorus. Unlike flat graphene, phosphorene has a puckered, wavy texture, giving it highly directional electrical properties. Current flow more easily in one direction than another. It's a semiconductor with a tunable band gap. Change the number of layers and you change how it behaves. This makes it perfect for transistors, photonic devices, and energy storage systems. It absorbs light efficiently, making it a promising material for solar cells and next generation batteries. But phosphorene is also delicate. It reacts with oxygen and moisture, so scientists are racing to find ways to stabilize it, bringing its remarkable properties safely into real-world devices. Each of these materials offers something different: a semiconductor, an insulator, and a tunable conductor. When combined, they form what scientists call van der Waals heterostructures. Atoms by atom stacks that can be designed like Lego at the nanoscale. Imagine building an entire computer chips by stacking these layers, each only a few atoms thick, where electrons, photons, and even quantum bits move through perfectly engineered landscapes. This is not science fiction, it's happening now in labs across the world. In electronics, atom-thin transistors made of MoS₂ could make circuits that are flexible, transparent, and far more efficient than silicon. In photonics, materials like HBN manipulate and emit light on the quantum scale, powering future communications and optical computing systems. And in catalysis, these 2D surfaces provide active reaction sites that could transform how we generate fuel, store energy, and clean the environment. They are not just laboratory curiosities, they are blueprints for the technologies of tomorrow, faster, smarter, and greener. From graphene to MoS₂, HBN, and phosphorene, each discovery brings us closer to a future where we can engineer matter atom by atom, designing the very building blocks of our world. The next revolution in material science isn't three-dimensional, it's two-dimensional. And though these materials are only a few atoms thick, their impact will be limitless. This is the future of energy, powered by nanotechnology. So that's all. Stay tuned for more in Nanoscience, Nanoworld, only with Sandy.